Once upon a previous millennium, there was a sacred notion that was shared between car enthusiasts, where front-wheel drive cars could only handle roughly 200 horsepower and nothing more. But where does this fear come from? This piece will cover the physics behind torque steer, which has plagued, in particular, many front-wheel drive cars of yesteryear, and the conditions which cause them, so you can diagnose and understand these loathsome feelings behind the wheel. We will also relay from both a daily and performance perspective why we want to reduce torque steer, and provide solutions catered to the specific drivetrain your car has. Lastly, we will discuss modern technological advancements which has resulted in torque steer being far less of an issue today. Without further ado, let's begin. Picture this, you're on a road trip jamming to some tunes with your mates and decide to change the song, letting go of the steering wheel in the process. Before you know it, your car starts veering in another direction into oncoming traffic. When there is too much torque being applied to the steering axis, whenever a force is applied on or by the tyre, we get torque steer. Anytime there is power to the front wheels being applied, whether you have a front wheel drive or all wheel drive, there will therefore be torque to the front wheels being applied, which would therefore be the prime suspect in inducing this loathsome feeling. Why is that? This is due to the difference in angular displacement of the drive shafts, which is equal to the torque applied to the shaft, multiplied by the length of the shaft and divided by the product of the axial moment of inertia and the material constant. We'll get back to this equation later in the video, but for now, let's move on. Okay, so we've gone through what torque steer is, but we have to ask ourselves the big question. Why bother with torque steer? Well, torque steer can still impact the intended serenity of the daily drive, especially in stop and go traffic or during merging and overtaking, where moderate acceleration is required, as your wheel can target you unpleasantly and unpredictably during these situations. Further, during long road trips on swathes of motorway strips, having to repeatedly adjust the steering wheel to keep the wheel straight can also make you a lot more tired than usual. This feeling can be further exacerbated by driving a higher powered front wheel drive vehicle, potentially causing an accident, injury or crash. For beginner drivers, this feeling can be quite scary, where the feeling is prevalent of the car acting against your wheel at times, just like Frankenstein. For the more enthusiastic drivers, let's explain why you definitely don't want torque steer in your setups. Let's first talk about drag racing or roll racing. If your car is steering all over the place like a wild animal, you're most likely going to lose, as your car is struggling to travel in a straight line and therefore not reach maximum speed properly. Additionally, during a track day or an autocross run, torque steer can hurt your lap times, as it prevents your car from staying straight under acceleration. This makes it harder to reach maximum speed on straights, ultimately impacting your performance. Not only that, but torque steer can also affect your cornering performance, as when accelerating out of a corner, the uneven power and torque distribution can cause understeer via reduced grip and an increased tendency for your car to pull to one side. These factors, combined with your steering feeling of being unpredictable and nervous, will hamper your ability to maintain a smooth and controlled racing line, as your car's handling, which will now require constant correction due to inconsistent traction of the front wheels, will be much harder to tame. Let's now seg over to the next section, where we'll discuss the factors contributing to torque steer. At the start of the video, we posed a question: why were people so fearful of front wheel drive cars exceeding 200 horsepower back in the day? Let's examine. In most front wheel drive and all wheel drive cars from days past, the drive shafts connecting the engine to the front wheels were of different lengths. As the shorter drive shaft transmits torque more directly due to being stiffer, the longer drive shaft would be more prone to torsional flex under load, leading to this unequal distribution of torque between the wheels. Many front-wheel drive cars in today's era still employ a transverse engine layout, where the engine is mounted horizontally instead of vertically, and an end-mounted transmission unit, where the transmission unit is positioned to the side of the engine instead of being placed through the middle. This combination, which aims for compact and simpler packaging, is unfortunately plagued by unequal length drive shafts due to one wheel being closer to the transmission than the other. Unequal length drive shafts and a transverse engine layout, which has an uneven weight distribution between the front wheels, causes the differences between the forces in the contact patches of the wheels, thereby causing a steering wheel to veer to one side. These asymmetries continue in other all-wheel drive cars as well. In all-wheel drive cars, it is often caused by the transmission being located off-center, due to the previously mentioned transverse engine layout, which in this case makes the half shafts different size. while Subaru have mitigated this issue via using a flat 4-boxer longitudinal engine layout paired with their signature symmetrical all-wheel drive system where all of the axles are the same length. Torque steer can still occur if two open differentials are used due to the driveline's clockwise rotation, thereby naturally directing more torque to the right side. During the 1980s, 1990s, all the way into the noughties, there was a boom of front-wheel drive hot hatches with turbocharged and high output engines, and given the lack of rigidity with the chassis designs at the time, which led to more flex under heavy loads, torque steer in cars such as the Mazda MX-6 GT Turbo was therefore pronounced. Older platforms such as the EG and EK Civics relied on thin steel and minimal reinforcement, meaning a lightweight chassis, which, whilst great for cornering, possessed limited structural rigidity, which made it difficult to handle high horsepower without dipping into the aftermarket and buying things such as roll cages. As many front-wheel drive cars within this era had either no power steering or hydraulic power steering, the steering systems offered limited damping and resistance against torque steer forces in comparison to modern steering systems. Torque steer also tends to get even more exaggerated when accelerating hard in low gears and in front-wheel drive vehicles possessing high horsepower and torque due to an increased overall reduction in ratio, which is the combined effect of the transmission gear ratio and the final drive ratio in delivering torque to the wheels. In this short clip, I am driving a Toyota Orion, which has hydraulic power steering, 268 horsepower at the front wheels with no limited slip differential, and 330 Nm of torque, and a transversely mounted engine on smooth pavement to account for even traction on each side. I've also recently got a wheel alignment on the car to ensure the issue is solely isolated towards torque steer. Notice, however, in the final values that there is a constant difference between the left and the right of 1 degree and 59 minutes, which is intended to correct the left pull exhibited by the car prior to the alignment. However, due to torque steer, notice how in hard acceleration, the car and the steering wheel still like to veer towards another direction due to torque steer. Let's play it. Whilst the scrub radius is usually kept to a small figure in front-wheel drive and all-wheel drive cars, its existence means that whenever a force is applied on or by the tyre, there is torque applied to the steering axis, and this effect is especially exacerbated with almost all front-powered cars coming with McPherson strut front suspension. You might be asking, what on earth is the scrub radius? Well, it's the distance between the centre of the tyre's contact patch and the point where the steering axis intersects the ground. This distance gets bigger and bigger, especially when the car gets fitted with wider tyres. Let's talk about parts in your car which, due to inherent wear and tear over time, can cause torque steer to occur. Worn edge mounts can also induce torque steer. This is as if the mounts aren't flexible enough to absorb vibrations from the engine. The transient movement from the engine during hard acceleration due to a high RPM will upset the crossway distribution of the car and result in unequal torque transmission to the drive wheels, leading to torque steer. A faulty differential, or in all-wheel drive cars, differentials, and faulty wheel bearings will also cause this unequal torque distribution to occur. Uneven suspension geometry, where camber, caster, and toe angles differ from side to side, as well as worn control arm bushings which will struggle to absorb some of the forces generated by the wheels, can lead to unequal wheel loading, leading to torque imbalances when accelerating. Wheel alignment issues and poor tyre and wheel installation can also cause these loathsome effects to occur as well, which is why we got one done before we accelerated our car. Now, let's talk about a scenario that could be very common in daily driving and track use, in cases where, due to either worn or deflated tyres, you'd end up using a space saver or full-size spare tyres, or tyres with differing sidewalls to left and right. In this case, when accelerating, torque steer will occur due to the unequal deformation between the left and right tyres. Why is that? This is as tyres consist of layers of ply, forming the structure of the sidewall, and as the ply design on your normal tyres different from the space saver tyre, or if you are using a different full-size spare tyre, this will mean the sidewall of one tyre will deform more than the other, leading to unequal torque distribution between the left and right tyres. Still confused? Think about it this way. You wake up and see you're going to be late to work, rushing. You wear two different shoes and you try to run so you'll make it in time. You felt off balance that entire run to work, and turns out you've now got some weird muscle imbalances because you naturally put more force on one foot than the other. This is just an example showing that different tyres on each side can cause torque steer. Low grip and uneven road conditions also exacerbate the effect of torque steer due to the reduced tyre traction. This is as in inclement weather, the uneven traction between the two wheels will mean an unequal torque distribution, pulling the car to one side even during light acceleration. Also, with the tyre's former ability to grip the road now being robbed in conditions such as the rain, any drivetrain imbalances mentioned will now be exaggerated due to the tyres being unable to generate force and friction to resist the uneven torque delivery, worsening torque steer. That being said, let's now cover how you can fix torque steer. To reduce torque steer, there are a couple of driving techniques that can help. The first one we'll cover is gradually applying throttle on acceleration instead of sudden, heavy acceleration by lowering the throttle. Whilst this has a negative impact on acceleration and lap times, the gradual application of throttle helps prevent overwhelming the front tyres, given the dual duties of managing both power and steering. The second one is usually mandated in many countries as a law of driving safety, and this is just ensuring you keep two hands on the wheel for full control of the car, as any sudden pulling of the wheel from left to right can be easily rectified without losing control of the car. Let's now move on to proper car modifications, which will be the biggest difference maker in reducing torque steer. Using harder bushings in the rear subframe or uniball joints in the control arms to replace factory rubber bushings, as well as stiffer engine mounts, is highly suggested, as they help minimize unwanted suspension flex and engine movement under hard acceleration. Harder bushes and uniballs provide less compliance in the suspension, which reduces the possibility of misalignment or unwanted deflection, while stiffer engine mounts, a popular mod on the infamously torque steer prone Mazda 3 MPS, help keep the powertrain securely in place. Whilst these are relatively cheap mods you can make to reduce torque steer, they come with the caveat of having a harsher ride and increased road noise emitted into your car, as despite their weaknesses, manufacturers often opt for soft engine mounts for a quieter driving experience. While adding an LSD is a great idea, considering it will usually limit the imbalances in torque between the two front wheels, in most commuter cars, their McPherson strut suspensions are not designed to accommodate the LSD. However, if you have a car with suspensions such as multi-link or front double wishbones, likewise the EG and the EK generations of the Honda Civic, and don't currently have an LSD installed, it will be a good idea to install in particular a mechanical limited slip differential, especially if you're going to do a B or K series swap in those particular Civic generations, as the high torque transmitted in those cars for the stock chassis, considering the low weight and moderate chassis rigidity for the time, will exacerbate this torque steer effect. A clutch type LSD is better for reducing torque steer during hard acceleration in high powered front wheel drive cars, as it can rapidly engage and provide a strong locking effect when there is a difference in torque between the left and right wheels, whilst helical type LSDs such as the Torsen, which uses gears to bias torque towards the wheel with more grip, are ideal for daily driving and for reducing torque steer in commuter cars. Meanwhile, 1.5 way LSDs offer strong locking engagement during acceleration and relatively mild locking engagement during deceleration, allowing for a more balanced approach of countering torque steer and smooth driving. On the other hand, two-way LSDs are the most aggressive in mitigating torque steer, but with drawbacks of more unpredictable handling characteristics during braking or lifting off the throttle, as it fully locks the wheels together as well during deceleration, making the car harder to drive in tight corners or during braking. Overall, whilst the LSDs are an effective solution, they are usually recommended more for mitigating understeer than reducing torque steer, as the general issues which cause torque steer are usually attributed to front suspension geometry. As we examined in the earlier sections, your front suspension geometry could be highly culpable for the torque steer occurring in your car. Let's first discuss adjusting your caster angle. Simply put, caster angle is how much your steering axis tilts by. Applying a higher caster angle improves stability and helps naturally self-center the wheels, reducing torque steer. One way you can adjust caster is via using adjustable arm. Given the commonality of McPherson struts in front-wheel drive cars, we'll use this as an example. In this case, you can use an adjustable tension rod that holds the lower arm in the wheel arch and adjust the screw so that the rod positions the lower arm backwards in the wheel arch to achieve a higher caster angle. Should you want a less adjustable but simpler solution, installing offset caster bushes is suggested, as when installed, the bush mounting of the lower wishbone and the offset center hole in a forward direction will move the arm backwards behind the wheel arm to give a more positive caster. However, too much positive caster can also create a significant jacking effect during cornering, placing more mass on the rear outside wheel, leading to unwanted oversteer. Changing your wheels for high offset wheels could also be a good idea, as high offset wheels move the wheel hub closer to the center of the car, reducing both the scrub radius and the torque arm length, resulting in the steering force being less impacted by drivetrain torque variations, therefore reducing torque steer. However, there is also a caveat to this change in regards to cornering, as usually a more aggressive or lower offset wheel will result in larger track widths, allowing for improved cornering speeds by keeping the tyre loads uniform, thereby allowing the tyre to generate increased lateral grip. Changing your tyres to high quality performance tyres which have high strength ply layers is another modification which can prove beneficial in reducing torque steer. Let's examine why, before we help you to identify these tyres in particular. As front-wheel drive cars have a tendency of the driven torque causing the sidewall to flex differently on each side of the car due to load variations, this can create uneven rolling resistance, amplifying the torque steer effect. In that sense, tyres with asymmetrical or directional tread designs with optimized sidewall plies distribute the driven torque much more evenly, minimizing this uneven rolling resistance in turn. Now, onto spotting which exact tyres help in particular. You could purchase run flat tyres and XL tyres identified by these specific labels. You can also buy ultra high performance tyres such as the Pilot Sport 4S or semi-slick tyres such as the Pilot Sport Cup 2, as well as checking the manufacturer specifications on the website for tyres which use sidewall strengthened technologies such as Michelin's dynamic response technology. In the case of inclement weather or crappy roads, you can also use all-season tyres with high strength ply, or even specialised tyres such as winter tyres, so that during scenarios such as hard acceleration, torque steer can still be reduced. Whilst the issue is not as prevalent as on FF cars, torque steer can still occur on all-wheel drive cars which have front-biased all-wheel drive systems like a Haldex and Mazdas. Often, as most all-wheel drive cars share many characteristics with front-wheel drive cars and aspects, such as front suspension geometry, we can assume that many of the solutions covered from the front-wheel drive section can also be applied to most all-wheel drive cars. However, let's now cover a modification which is exclusive only to all-wheel drive cars, and this is by passing part of the torque to the rear via a button or via your infotainment. A solution from our old understeer piece, this change now instead reduces the torque to the front wheels, so the intended result is actually a lower difference within the torque distribution between the two front driven wheels. Earlier in the video, we examined the conditions which can cause torque steer, but I'll raise another question. Why are so many front wheel drive cars today, like my Toyota Orion and the newest Honda Civic Type R, pushing well over 260 horsepower, despite previous beliefs suggesting they couldn't even go over 200 horsepower? Well folks, in the modern era, due to the massive difference maker being automotive engineering, torque steer is far less of an issue than it was 20 to 30 years ago in the golden age of cars, where manufacturers were making engines so strong that the chassis couldn't keep up. Let's first refer back to that torsional twist equation we wrote down. Assuming the drive shafts are made of the same mechanical properties, torque steer arises when the left and right drive shafts have different lengths. Using equal length drive shafts ensures that this torsional twist is the same on both sides, balancing torque delivery. This is done by using an intermediate shaft on one side of the transmission to effectively equalize that drive shaft length on both sides. This is one of the most significant changes that most modern cars have implemented to reduce torque steer, starting from front-wheel drive hot hatches such as the Mark II Gold GTI in the 1980s, and in Honda's situation, higher power front-wheel drive cars such as the Accord, Prelude, and eventually the EK9 and DC2 Type R in the 1990s. Over many years, front suspension geometry has been optimized and improved to deal with high power front wheel drive setups, in particular dealing with lowering the scrub radius number as close to zero as possible. This trend started with the introduction of Ford's revolutionary rubber knuckle system in 2009 in the Mark II Focus RS, with Ford's design shifting the steering axis by using an additional knuckle that connects the steering arm to the suspension in a more complex manner. However, the most lauded development in reducing torque steer to near zero was Honda's dual-axis strut design, unveiling it in 2015 in the FK2 Type R, which produces an otherworldly 306 horsepower and 400 Nm of torque, only to the front wheels. This design differs from conventional steering axis designs with a strut tower and lower ball joint, as it instead uses a separate hub carrier with two extra ball joints acting as the kingpin, therefore separating the strut from the steering axis. They have also set a higher caster angle by tilting the steering axis back further than the normal suspension. With this design, which is also being adopted and improved upon in the newer FK8 and FR5 generations, achieving a near zero scrub radius, Honda engineers have quoted that they have eliminated torque steer by 55% compared to standard suspension design. Another prominent change was the introduction of electric power assisted steering systems, which is used in the overwhelming majority of new cars today. Conceived in 1995 on the Suzuki servo mode, its widespread use began in the early 2000s with the 7th gen Honda Civics and the E120 generation of the Toyota Corolla. EPS systems use torque steer to detect uneven forces in the steering rack, then apply a corrective steering torque to counteract torque steer to ensure the steering feels balanced. Unlike the hydraulic steering systems of yesteryear, EPS allows for software-based tuning within the rack itself, allowing the torque steer effect to be directly suppressed at the steering wheel. Finally, there has been significant development in making highly rigid front-wheel drive and all-wheel drive platforms which are specially designed to handle high horsepower and torque. Most modern platforms, such as in the FK8 Civic Type R, use advanced materials such as ultra-high strength steels, as well as structural adhesives and reinforcement beams to improve chassis rigidity further to withstand high power and torque loads during hard acceleration and therefore allow for stability. With that being said, let's head into the concluding remarks. Before we conclude, I'd like to thank each and every one of you for all the support on our last understeer piece, and especially if you made it to the end of this one. Wow, this was a long piece. I'd say this was much more of an engineering deep dive than the last one, and researching all the info for this one honestly took quite a while. I hope you all learned something from this video, so that your car doesn't go all wonky, like when you take your dog on a leash for a walk and it starts running in different directions. Much love to you all, I'll see you in a bit.